please do. Thank you, Peter. Hi, this is Rick Marshall. I guess I'll be your host today. This is a talk about Vista architecture modernization, and it's based upon the recent work that we've been doing for the VA PALS project on modernizing the error log. I'm an architecture expert in Vista. I'm not the architecture Vista expert. There's a number. Oh, I see Michael's call. There we go. Mute. I see that some of the other great Vista architecture experts are either involved with this peripherally or are actually on this call. I want to call out Cameron Schlehuber. He's one of the great Vista architects, as he was the Vista database administrator for decades. Many of the things that I'll be talking about as desirables or that you'll be seeing kind of being done in the modernization come from initiatives that he started at one time or another, trying to get us all to stop writing single character variables and go-to loops and try to make maintainable code. So all hail Cameron. Thank you for joining us. And then the code base itself was originally created by Joel Ivey and was maintained at times by Wally Fort, and both of them are also incredible Vista architects. So I'm just one of many here, but since I've got the floor today, I guess I'll be your guide for this discussion. So we're talking about legacy software. So let's deal with it up front. Most people use the term legacy software as a curse word. It's used to create marketing opportunities. If somebody has functioning software that their business depends on and does what they do, and you don't know how to crack that market, you shame the managers and tell them that they have legacy software and it's bad and it's old. And there's often at least some kernel of truth to it. There are often things wrong with legacy software, just like there are with all software. Brand new software that you just bought, you have the opportunity to not know what's wrong with it because you just got it. And legacy software, you're more likely to know what's wrong with it because you've had it for a long time. So it creates a perception issue. But what we need to do is acknowledge that if we're thinking more carefully about what it means to be legacy software, it means that the software is actually working in production and that it's been working for a long time. There are many kinds of bugs that only come up sometimes, and you're only going to find them in your code if you've been running your code long enough to find it. So legacy software is code in which all the main paths that you've gone through, the algorithms tend to be very well tested by comparison with fresh, shiny new code. And also, people frequently judge legacy code in terms of today's priorities and not in terms of the priorities at the time it was written. Most code that we run on our PCs or servers today would not have run at all in 1988. It just would have been a complete failure. And so very, very smart people worked very, very hard to make the code look the way that it looks when it's legacy software. And the missing piece that needs to be done for modernization is to recognize that we have working algorithms, and what we need to do is take into account the change over time and upgrade it. And what we'll find is that the process of upgrading, if it's done correctly, allows us to preserve everything that works while adding the desirable new features of modern architecture. If we start over from scratch, we throw out all those lessons that are buried in the code. Thousands or tens of thousands of little points of wisdom that make the flow work the way that it does. So one of the ways to illustrate that difference is to take a look at the differences in code memory, speed, user interaction, and network interaction from the 1970s. Late 70s were when some of this code began to be written to today. The error log in particular was written in the late 1980s, early 1990s by Joel Ivey. Prior to him writing this, we didn't have a kernel error log. Each mumps implementer had their own error log and their own browser to read it. And the problem we ran into is as we hopped from system to system doing support, each of the implementers' browsers worked differently than the other ones did, and it created problems for us. We would have typos. We'd have to relearn. How do we look at our errors on this one? And of course, examining the errors and monitoring problems is one of the fundamental activities for system support. You want it to be streamlined and work well. So Joel's first action was to write a universal error log browser that could browse any of our mumps implementers' error logs and present it with the same UI. And that was fabulous. And then in the next version, he said, well, having done that, it would be even better if he created his own error log file so that he could make sure there was consistent information being stored in there that he could then show in the browser. So the subsequent version was the one that introduced the error log file as well. And by that point, we'd switched over completely from using implementer-specific error logs to using our own kernel error log. So the time frame that puts us in is, pretty early on in this diagram. And over the decades since then, because the error log works so well and the browser works so well, although there have been changes all the way up to the 2000s, there haven't been a lot of them, which means that the fundamental code base is still, late 1980s, early 1990s era mumps. Now, the main line that you guys need to know about, for those of you who don't have the background, is that the mumps standard was originally put out in 1977. It was updated in 84, in 1990, and in 1995. The 1990 update is the one that introduced variable scoping, modern algorithm structures, parameter passing, functions, you name it, all the things that you need to create complex systems in which you properly scope your information. And this code was written mostly without that. So it makes an excellent example of modernizing Vista legacy code because it involves reaching all the way back to basically 1984 era mumps, even though it was written a little later than that. You can find, as we'll see when we look at it, you'll find spots here and there that use 1990 or 1995 era mumps, but most of it is perfectly cromulent, absolutely sound, and completely cryptic 1984 era mumps. But we have opportunities now. This is what Vista Modernization is about. Because our environment has changed so much, because we have so much more computing power to work with, many of the sacrifices that were made at the time in order to make it work correctly, they're not necessary anymore, and we can update that. So what are our strategic goals? So first of all, you do want to whenever you look at a piece of Vista software and you're thinking about modernizing its architecture, your first question has to be, is it still applicable to the business logic and flow today the way that it was when it was written? What's changed about the way that we do business and about the way that we, for example, troubleshoot errors? What are the differences today? And is the layout of the prompts or the choices, is all of that still appropriate? And anything that's not should go on your checklist of things to change. Next up, which is the one I've been emphasizing in the slides so far in the discussion, is reprioritizing your software quality trade-offs. You can't have everything. Many things come at the expense of other things. So you have to choose which qualities you want. You want readability, you want writability, you want efficiency. Do you want it to fit in a small space, in a tiny little slot of memory? Does it have to be really lightweight because you're dealing with PDP-11s for your processors, or do you have incredibly powerful processors so that you can sacrifice computing power in order to achieve other goals? You have to balance what your priorities are. and decide what your trade-offs are. So this is one of the things that is almost consistently changes when you modernize architecture. If you look at the difference between when you wrote it and how things are today, you'll almost always find that it's time to rebalance those trade-offs. And that'll be one of the major drivers for how you modernize the software. By the way, when people talk about modernization and legacy software, they almost always skip these steps. They almost always go right to, and I happen to have a solution for you right here, and it'll only cost you $16 billion over the next 10 years or more. They don't really want to talk about this stuff, because the more you talk about this stuff, the more you start making a decision on the basis of what actually are your needs and how much does your legacy software already meet them. This is good for us and not so good for the salespeople, as we will see. Then there is code therapy itself. Because of the trade-offs that were made in 1984 era mumps, a lot of code is not very readable. Frequently it's not very maintainable or changeable either. It's often very brittle. It works great. There's nothing wrong with it until you go to try to update it. And when you try to update it, you'll find and I say this with love because I've written plenty of this software myself, a rat's nest of interdependencies, such that if you try to change one line, you'll break 16 other lines. They're all passing flags to one another. There's go-tos all over the place, so that when you change this, it can be very difficult to figure out what the ripple effects will be. And if you don't know what the consequences are of the change you're about to make, then it's not safe to make the change. So one of the big things you want to do is do some code therapy to clean up the code in the sense of making it easier to change. And as part of that, you want to be thinking about what's changed. One of the advantages of doing a project like this is you look back over time, you see how much has changed since 1988, and then you can project forward and say, no matter how modern I make my code right now, no matter how good a job I do, I need to be thinking about how about 35 years from now. How will computing have changed, and what kinds of changes will I wish that I could have made, and where are my points of brittleness in the code the way that I'm planning to design it right now? And if you think about that, you can future-proof. You can avoid making unnecessary dependencies. And if you do that, it sets you up to make the code easier to change as you go forward. Another category of changes here is I/O issues. This is one of the ones that's most obvious to people when they're decrying legacy code, when they're saying that it's a labyrinth and you shouldn't bother trying to fix it, and we should just spend more than our annual budget for the next 10 years trying to buy a replacement. Frequently one of their arguments is, well, it's locked into the terminal. It expects there to be a terminal. It wants to do reads. It wants to do writes. How are we ever going to make this thing be on a GUI? How are we ever going to make it for the web, or for VR glasses, or holograms, or haptic interfaces, or whatever the next thing is? How are we going to do that? They'll say, well, it's impossible. If it's on the terminal, it can't be done. And I've just proved it can. And I'm not the first to prove it. Anybody who has thought carefully about I/O architecture and software has come up with strategies for how you can make these migrations and transitions. So part of what you want to do for Vista Modernization is take code that's locked into the terminal, assumes it has the terminal at its fingertips, and transform its dialogue with the user to be table-driven so that it can be translatable. And that will also make it testable. You can't have unit tests when things are reading and writing from the screen break down. But if you can get it to where you can switch it so that the output could go to an array, or the input could come from an array, then you can test the subroutines by loading up the input array and checking the output array afterwards. You do all those things, and it turns out those are the same things that you need to do in order to prep your software to go to a GUI, or to go to a silent interface to another system, like over the broker, or to the web. And if you make those changes, what you discover is that you've released an enormous logjam of modernization. There's a whole bunch of things that become easily possible once you address that. There's a similar issue around database accesses. If you look at your file structures and you say, these were great for 1988, but now I'd really like to update it in the following ways. Maybe there's some new database theory, and there's a bunch of tools that can manage things that comply with that database format, but my files don't. I might want to change my files. But the problem is, if the accesses to the files are happening all over the software, then it means if I make a little change to the database structures, again, I could break 16 different places in my code. So what I want to do, just like I want to collect all the reads and writes into one set of subroutines in one place where I can make them switchable, I also want to collect all the database accesses into one module where it's all controllable, and where I know if I change something in the file structure, I only have one place to look to locate where I want to make changes. There's two others that aren't on this slide, but I want to mention in passing. And I've alluded to one of them, and one of them is unit testing. Modern software should come with a complete unit test suite. This is part of the OSEHRA certification levels. It's expected now. It's the way it should be, but most of our production code doesn't have suites of unit tests in production. And following the principle that Mike Henderson gave us some years ago, we believe that software should ship with its unit tests. We believe that the end user, anytime they want to, should be able to run the unit tests and confirm that the software works. Why should they take the salesman's word for it that the software is perfect and has no bugs? Why should they take the developer's word for it? They should be able to run the unit tests themselves. And that also works well for patching. If they can run the unit test before a patch, see what the results are, then they install the patch and they run the unit tests again, then they can isolate if the patch introduced difficulties. So it's a great power to the adopters of the software if the unit test suite is with them. We don't think anything should count as modern unless it comes with its unit test suite. And then along with that, another standard that we're moving towards is timers and performance monitoring. It is frequently impractical to try to get a quick answer to the question, is my code fast? Is my code fast or slow? Well, relative to what? On what kind of computer? And when we say code, I might have, 100 subroutines. Which subroutines are you talking about? Are you asking if they're all fast? If they're all slow? It's too vague a level of discussion about performance. We really want to have timing information on all of our subroutines. And to get that timing information, it may take seconds or minutes or hours even to run 10,000 passes over the subroutine to get results that we can do minimums and maximums and averages on. So it only makes sense for the developers to do that work, document it in the code where it's accessible to anyone who wants to look at it, and also ship the timers with. And for that matter, you ought to be able to do real-time performance monitoring. You ought to be able to throw a switch on your system and say, I'd like to collect performance data right now in my production environment while this code is running, so that I can see if my timing information deviates from what we were expecting, from what was promised to me. If I can't do that, then again, I'm not so much an adopter of the software who's empowered as I am a hapless consumer who's just having to take on faith everything that I'm being told. So we think modern code has to ship with unit tests and with timers as well as these things here. These are our fundamental strategic goals. And what we discover as we go through this is that how much change you have to make to modernize depends entirely upon what generation your software is at. If you look at how algorithms are structured, and you look at how variables can be named and scoped, and you look at how databases can be structured, you'll find that they pass through generations of improvements. So in the case of variables, this is really easily demonstrated here. I'm going to run you through this real quick. In the old days, we only had 2,000 characters for a routine, and we only had 2,000 characters for the symbol table. It does not take you long to burn up 2,000 characters. All your computations had to fit in that space. 1984 standard raised that to 4,000. The 1990 standard raised it to 5,000. The 1995 raised it to 10,000, and now we're operating at we've loosened that since the 95 standard. But much of this code was written back when 4,000 was the standard. So to make your complex medical software that's trying to assist you with diagnostics and not kill anybody work correctly in a 4,000 character symbol table, you are abbreviating like crazy. You're abbreviating every variable that you can, and you're attempting not to create new variables if you can possibly avoid it. And so you find a lot of use of variables like I, J, and K for loop variables, and a lot of X's and Y's for inputs and outputs. And you'll find that variables like X's get reused over and over and over and over because they're desperately trying not to open up another variable. Right? This is not readable code, but it is miraculous code because they were able to get such complex algorithms into such tiny spaces. But that's no longer our restrictions. We shouldn't be writing code like that anymore. It's no longer necessary. It doesn't bias anything. The next generation is where we say, well, maybe it's okay to have more variables, but we still don't want the names to be very long because the routine size is constrained to 4,000 characters. And so that's when you start getting people using single character descriptive abbreviations like D and M and Y for date, month, and year. right? We're no longer insisting everything cram into X if we can possibly pull it off. We're loosening a bit, and we're starting to have mnemonics. But D could stand for anything. You hope that you're in a date-time conversion utility so that you can say D will always be the date. But if you're in a big subroutine that does a lot of different things, some of which is date conversion and others is other things like diagnostic information, which one is this D? Well, it's hard to say. So this is also cryptic. Abbreviated names tend to come next, and then that's we run into the era where Cameron Schlehuber and the hard hats, the first generation hard hats, did us all such a favor, and that was when they came up with the namespacing system. The namespacing system made it possible to run different modules in the same process, as long as they stayed out of each other's way in the variables. So we had to name all of our routines so that they had a prefix that was unique to our application. And we had to name all our variables so they had a prefix that was unique to the application. And that way FileMan could call lab, could call pharmacy, and we wouldn't step on each other's variables because we were using different names. DI for FileMan, LR for lab, PS for pharmacy, and so forth. So this was a major breakthrough for us, and we couldn't have done it without those guys coming up with it. But this often lends itself to cryptic names as well. I mean, DIC, DLego, LR out. You may or may not have any idea what these are talking about. So the 1990 standard, which was the big breakthrough for mumps, for modernizing mumps, gave us the new command, which allowed us to scope our variables to protect whatever it was set to before we were called and ensure that when we quit, it goes back to the way that it was. And it introduced parameter passing, so that the caller doesn't have to call the variable the same thing that the called subroutine calls it. They can have two different names for it, which eliminates the need for namespacing in some senses. And it loosened up. It increased our size to 5,000 characters. It loosened up the sense of being cramped, and we gained the ability to say, maybe we could actually have variable names that say what they mean, like month. And then for special cases, like when we're passing a handle to the variable and we're trying to avoid stepping on each other and creating very difficult to diagnose bugs, we would still use namespacing. We'd still use a DIC in a case like that for FileMan. So you can look at the code. You look at a piece of software and you can tell by the naming strategy used in the variables what generation it is. There's one more generation, and that's the generation we'd all like to move to now, which is where we can use lowercase and mixed case. This is allowed by the VA standards and conventions under most circumstances to create truly readable names. Right? Lowercase was a great, for those who don't know, lowercase was a great breakthrough that the Byzantine monks came up with for Greek. God bless them, because it turns out it's not that easy to read and write in uppercase. It's like being shouted at all the time and shouting all the time. But with lowercase, with the ascenders and descenders, you get flags, you get more distinctions. The code is vastly more readable. And then we would stick to the uppercase and the namespace where necessary, again, for those special circumstances like where we're passing handles to a variable. So we want to migrate downward. Right? We want to migrate from the older methodology that was imposed on us by the restrictions on the software to the more modern methodology that makes the code that mumps can't, people criticize mumps for not being readable, but the truth is old cryptic mumps where we were achieving miracles of computation in tiny little computers, that was cryptic because that's what we had to sacrifice in order to pull it off. Modern mumps can be as readable as any other language if you spell everything out, if you use mixed case. There's no reason why it can't. And readability and plays right into writability. It plays right into testability. It plays into the ability to troubleshoot the software. All of these things increase the performance of the programmers. So this is a huge part of modernization. The software complexity is more manageable if you can see at a glance what everything is and you don't need big deciphering tables. You can get better control of your variables through scoping than you could through sets and do's and kills. And one of the biggest things, and let me just take a second here. One of the biggest obstacles to being able to modernize or change your software is whether or not you can understand it. And when you're trying to understand the software, as hard as it can be to understand the algorithm, which is what people talk about all the time, the far harder thing to understand is how many different pieces of information do you have to keep in your head at the same time? Because they're what drives the algorithm. And if you don't know which of these variables apply to the current lines you're reading and which ones don't, you're in trouble. if you try to change things. It's one of the hardest things to manage, and part of the reason is you could be looking at one line of code, but there could be 76 different local variables passing through this line of code. And if it's doing anything indirect, you especially don't know which of those variables are coming into play. So one of the most powerful things you can do to modernize your code and get it under control is to shift from a strategy in which variables are just all over the place in a great big pool from beginning to end, which you see in old code where they have a kill at the bottom and it's a gigantic multi-line kill that kills a pile of variables. The error log did that. Or you'll see it in quote-unquote semi-modern code from the 1990s where people aping declarative languages would use a new command at the very top of the routine and new, again, an enormous long list of variables. And the problem with doing that is it doesn't tell you where these variables are used. It means that every single line of code you have to think about all those variables and which ones might possibly be coming into play. What you really want to do to simplify the code, to shrink down the complexity to something that you can keep in your head is you want to tighten up the scope of your local variables so that they get newed, set, used, and disposed of immediately. You want the narrowest, tightest possible scope so that you can look and see, well, I don't care about this variable because there's the quit that got rid of it, and I don't care about that one or that one. I only care about these what might have been 76 variables might turn out to only be 3 that matter. And the other 73 were used temporarily for short-term purposes. In the old style of scoping, where you scope across the entire subroutine, you can't see that unless you understand every line of code so that you can rule out that it was used anywhere else. But in the new modern form of scoping, where you scope tightly, you can tell at a glance that none of these other variables are relevant, and this is the only 3 that you have to care about. Distinguishing the foreground from the background, distinguishing the tactical from the strategic, distinguishing what are your internal private variables from what are your interface variables that have an impact on your callers. These are some of the most important things you can do to gain control of your code. And how you write your code directly influences whether people can pull that off. So this is one of the most important parts of modernization. Again, you will never hear a marketer tell you about this. They don't want you reading the code and getting power for yourself. They don't want you to be in control of your fate. They want you to be dependent and give them money as much as they ask for. And they'll decide whether or not to ever give you any upgrades. But if you want to be in a position of power, if you want to be in charge of your own fate, you want to get into this code and get control of it. And the local variables are an important place to do that. Another place to do that is with your layout of your subroutines and routines. What are the relationships? Now that we've talked about data, let's talk about the algorithms for a second. Even before we get into questions like exactly how did you lay out some lines, which I'm not going to get into too much. Just the question of this subroutine does this step, that subroutine does that step, the third subroutine does a third step. Where do you put them? How do you name them? Where do you lay them out? And how many routines are you putting them in? And what are you calling your routines? What is your basically, this is the book. This is the library problem. How many shelves do you have, and where are you putting your books? And are you just scattering them wherever you happen to have been sitting at the moment, or do you actually have some schema so that some new person could walk in if they were looking for a book and sort of figure out what your system was and find it? This has a huge impact on the comprehensibility of the code and your ability to change it and therefore modernize it. So if we look at how packages typically evolved, they go through generations as well. The first generation is I have an idea for an algorithm, a feature set, and it's only going to take me one subroutine, so I only need one routine. So I know exactly where to find all of the code that is responsible for this feature. It's in the one subroutine that's in the one routine. So far, so good, right? Anybody who ever programmed in mumps or any other language started out with something like this. But then, as you add features, you add more subroutines. And, Vista and mumps impose length limits on routines because, unlike programming on your personal computer, you have to share these production Vista systems with, thousands of other users who are on there at the same time. You can't use up all the RAM. And so we have restrictions on how many variables you can use and on how many routines you can use. And once you add more subroutines, then there is room in that restriction. You have a problem. And this might sound obvious to the mumpsters among you, but the question is, how do you then decide what to call your next routine that you make? Because, Kitty was a good name, but, this is also Kitty, but you don't have room to put it in Kitty. And so you see this sort of desperation move. It's a reasonable desperation move to say, well, then this will be Kitty 1, right? And I'll just put half the subroutines in here. And then, I add more to the first routine, and now it's out of room again. And then, so I move some of those over to Kitty 1, and I don't yet have a problem. But, I add to both of them, and now I'm out of room in both of them. And so what do I do? Well, that's when the crazy sets in. And I mentioned this because this is what happened to the error log. This is exactly the path of evolution that the error log went through. There's an XTER routine at the top, and then eventually they were running out of room. They made XTER1. And there's good stuff in XTER and good stuff in XTER1. And then they said, oh, I need more room. They made an XTER2. But then they were sort of like, okay, now I really understand what's in XTER, XTER1, and XTER2, but I need to add more stuff to XTER1. It's really in my brain conceptually belongs in there. So they made XTER1A and 1B. And then 1A filled up and there wasn't enough room in there, so they made 1A1. So when we say the crazy sets in, I want to say there's nothing wrong with what they did per se. I did the same thing in Taskman back in the day. This is exactly what happens when you're thinking about the older methodology for naming and it doesn't work anymore. But you're trying to make it work. And frequently it's because, a site called with an emergency and you got to get a patch out. You don't have time to back up and say, well, let me come up with a new organizational schema for all my routines that will give me room and logic and all that. It doesn't work. But at some point, you do need the time to be able to sit down and rethink what, from an object-oriented perspective, is a logical, intuitive way to lay out my subroutines. Maybe there's some stuff that's about the human being. Maybe there's some stuff that's about the actions that the cat takes. Maybe there's some stuff about the relationship between the cat and other critters. You sort of come up with an object-oriented design, and you lay out your subroutines according to that, and you've solved half the problem. Now, it is much easier to figure out that pet is going to be under kit human and not under kit critter than it is to figure out that pet might be in kit 1A3, right? I mean, there was no intuitive way to know. Now there is. So there's a second problem we want to solve as well. Even when you solve this problem, we have a problem with interdependency. Which of these subroutines call which other subroutines, right? And the more these subroutines call one another, which on theory is supposed to be the promise of modular programming, the more you end up with a situation where if I want to rename this subroutine, it's going to have an impact on all of the other subroutines that call it, because I have to change their calls to match my new name. And what if I want to rename the routine? Now it ripples out across all of the subroutines that are in here and all the subroutines who call them. There's this kind of massive ripple effect that discourages people from rationally reorganizing their subroutines and their routines because it's just too much labor. We happen to have a small proposal for a way to solve that, and that's that you create, this is the third generation of how to organize your routines. You create an interface routine. All APIs, all options, all remote procedures, anything that calls into our module will only call into this routine and not touch any of our other routines, right? So no external application cares or knows how we've laid out our library of software and subroutines. We could rename and reorganize to our heart's content, and we won't have to check with any other application developers. Well, that's all well and good, but it still leaves us in the situation where we ourselves might be the one that has the ripple effect. We might be wanting to move a subroutine that 18 of our other subroutines call. And so, we're the one that doesn't want to do it. So again, just like you're putting your public interfaces in this interface routine, you can put your private interfaces in this interface routine. If more than one of your subroutines calls, if you've got a subroutine that's called by more than one of your subroutines, then you think of it as a new category. Just like there's an API that's an application program interface, you think about it like a private program interface. And the private program interface is treated differently than a truly private subroutine. A truly private subroutine only goes with the subroutine that calls it. They can be a unit and they can move from routine to routine together. But if it's called by 2 or 3 different subroutines, it's really a shared resource. And you should treat it similarly to how APIs are treated. So you put its label over here in the interface routine, and you call the interface routine instead of calling it directly. And the more you do that, you'll get yourself into a situation where your subroutines don't care how you've organized the other subroutines, right? It's like they're either calling something private that's always going to be right with them in the same routine, or they're calling something that's shared, in which case they're calling it through the gateway routine, and the gateway routine is the only one that needs to know where you put it. So now, whenever you reorganize your routines and subroutines, you only have one place to change. When we look at the code, you're going to see that we've done this to the error log. The error log now has an interface routine, and we've re-schematized all of the routine naming and all the subroutines where they're laid out and what they're called. And whenever they're calling a private subroutine in their own routine, they can do it directly, but if it's a shared resource, they call the interface routine just as though it were an API. Please. Yes. Yes. It means that the subroutine name is no longer a permanent contract guaranteed to God between now and eternity. It can now be something you can easily change. Yes, it stops being kind of rigid and starts being malleable. So, there are. I'm just going to actually pause here before I go on, just to show you a picture from the code so that you can see that it matches what we're doing here. If I go to okay, so this is the old code, just at a glance. This is XTER1, right? Very horizontal, very abbreviated. This is XTER, the top level routine, and there's parts of it you can see immediately what they do. This is a bunch of help text down here, but there's other parts you look at, you're like, what? And if you look, you'll see a lot of go to commands. You see that G there? Go to, go to, go to, all over the place. I mean, this is spaghetti code. It's very well designed spaghetti code, but it's spaghetti code. There's go tos all over the place. All these subroutines are in each other's business, right? You can't change anything without changing all the subroutines that are in their business. But the modern version of this routine, XUER, this is our interface routine. It is both the entry point for the main browser option, and it's our interface routine. So if I scroll down past my commentary, which we'll talk about later, the whole structure of this routine consists of nothing but little interfaces, one after another, like so. And some of these, like the option interfaces, are public. They're being used by MenuMan, or they're task interfaces being used by TaskMan. But others are private. These are PPIs, private code. Nobody uses get of XUER except XUER himself. His own subroutines use get of XUER. But so many of them use it that it didn't make sense to have this be... It was never truly a private subroutine. It was being treated as one, but then all the other subroutines were calling it, and they were all locked up together, so I couldn't move it without breaking all of them. But now, if I decide to move it out of XUER FEG to someplace else and rename it from get to something, maybe I call it load, right? This is the only place in my entire module I have to change. I can do that move, change this one thing, I'm done. So this encourages me to reorganize and rethink, right? I no longer have a punishment ahead of me if I consider making a change. It becomes easy to modify the code. It becomes malleable, and my productivity goes up. So this is why we're talking about this, is that this third generation of routine organization in which you concentrate all of the interfaces into one place, it raises your power, it raises your flexibility. So, all right, let me go back to the presentation here. So, moving along, systematizing abbreviations, right? You know, the Marines have a rule that says if you're doing a presentation, they have a rule of 3. You should only say 3 things. If you say any more than 3 things, somebody in the audience is not going to remember the 4th thing. Some of them might, but some of them won't. So, don't go beyond 3. There's another rule that's used in menu management theory called the 7 plus or minus 2 rule, which is that if your menus are too short, then you can't fit enough items on them, and so you need more submenus and more sub-submenus, and now people get lost trying to remember how much they have to navigate down to get to the thing that they want to pick. But if your menus are too long, then they can't remember all the things that are on the menu, and it takes them time to scan it and find the thing that they're looking for. It turns out what this is discovered, they found that the sweet spot is 7 plus or minus 2 items. And that's because the human brain can handle about 7 plus or minus 2 short-term memory items at a time. You try to do any more than that and you can't remember it. The problem is when we're designing algorithms, we often have, well, almost always have more than 7 plus or minus 2 things that we need to organize. So how can you organize things in a way that people can remember them when they can't keep track of very many things at a time? It turns out there is one thing significantly longer than 7 items that every English speaker has in their head, and that's the alphabet. If you use the alphabet as a mnemonic, you can hook organizational schemas onto it to make a system of abbreviations such that people can remember large numbers of things for where things are stored. So when you're doing a reorganization in preparation for modernization, one of the things that you want to do is come up with a naming schema by coming up with an alphabet for what the main object-oriented ideas are in your software. I've done this for Mesh, I've done this for Taskman, I've done it here for the error log. It was one of the first things that I did once I sort of scoped out all the pieces that were involved. And so I had to think about, okay, if XUER is my namespace, that's my interface routine, right? We make it short and sweet to get to the interfaces. But after that, what are my main ideas that I'm capturing? And kind of what I settled on is I have some options that I support. So they're all under XUERO. And if I have protocols or remote procedures, I want to leave room for them. And then the error trap itself goes under XUERT. This is the thing that is part of the foundation, the safety net under every Vista process running. And then I need room for unit tests and other utilities, so they'll go under U. So, and then I'm going to put a web interface on this thing now that I've done the first generation modernization on it. So I need a place for the web. So all my web stuff is going to be under W. And then I need an installer that lets me switch back and forth. I've noticed that even though the existing software is under XTER, I wrote this under XUER so that I can put the new software in the same environment that's running the old software and run them side by side. And that allows for testability and rollback capabilities. This is incredibly important. So I have a installer routine, XUERI, that I can run that will repoint all the options back and forth between the version 8 routines and the version 9 routines, depending on which one I want to test. So I got that idea from Taskman, where we did that for Jordan as well. If I need HTTP RESTful services, I can put them under H. I remember file management, collecting the file management in one place is something you want to do, so I put all the file management under F. I've put all the dialogue, the reads and writes under D. And one of the big innovations that I have going forward for modernizing the error log is I want the ability to flag errors as the error that I'm currently troubleshooting and trying to fix. And while it's flagged, other people know that I'm working on it. And I'd like it to be the case that if I come out with a patch, the patch can be tied to the error so that when you install the patch, it finds that the error has been resolved. It deletes all excess copies but one and saves that off in an archive file and shows that, okay, that one's done. Because one of the problems we have now is the error log chews up your disk space, and when you install the patches that resolve the errors, there's never any relationship between the active installation and cleaning out your error log. But there should be, and there could be, and it'd be easy, and I'll put all that software under A for archive. So you see what I mean about an alphabet. And then underneath that, you can sort of lay out all my reads are going to be under XUDRD, all my writes are going to be under XUERDW. You know, you can come up with what it is, but you need to have a schema to tell you where to put things. So that covers kind of some sense of what we're talking about. You come up with a schema for organizing your software, and you're going to find you're much faster at changing it. And because you're much faster at changing it, you can make in a short time changes that managers and salespeople told you were impossible and couldn't ever be done. But instead, you're able to pull it off because you're increasing your speed of production. So these are currently the 36 steps that I went through on the error log. In truth, I've only really gone through 6.5 steps, of which these are sub-steps. But we've decided not to try to simplify things by making it a run-through. The most important step is to decide what is the scope of your work. You know, with complex integrated systems like Vista, it's very easy if you don't draw lines and say, this is where I work and this is where I don't work, to follow the threads from one module to the next and find yourself, updating God knows how many things. You really want to set yourself a doable scope of work for your modernization. And when you set that scope of work, make sure that you don't forget about the things that aren't routines. Remember your data dictionaries. If you've got files, your data dictionaries might need updating. Your data might need updating. If you've got options or remote procedures or protocols or other non-routine elements, those maybe need to be included in it. And when you're doing the work, you also need to think about what version of Vista are you working on and what dialect of Vista are you targeting. Is this for RPMS? Is this for VA Vista, OSEHRA Vista? You need to pick your targets and constrain it clearly. And the reason you need that clarity is that when you're deep in the middle of refactoring, it's very easy to get confused. Your brain is overwhelmed. You're thinking about so many things at the same time. So you need other things to be as crisp and clear as possible. Having a crisp frame makes that possible. Another thing that you really need to do is make a change log. And the reason you need to make a change log is it's easy to go in and fix a bug in a routine without actually changing anything. But if you are overhauling the routine from top to bottom, then every single variable, every line of code, every command, every function, every relationship or call, all those things have got to be, you have to keep track of them. You're pulling things apart and putting them back together, and if you forget any of that, you're going to drop ends and you're going to create bugs. And if you do this perfectly, if you do the best job you possibly can, you will still drop threads and create bugs because this is such a complex process. But if you create a changelog and keep it up to date as you go, you won't drop very many of them. And when you find the bug, you'll be able to figure out what the cause was and deal with it very quickly. So yes, yes, it helps you to work as a team too. I mean, if a team does this, you can handle bigger projects than just something like the error log, which is a one-man job. So then at the tops of your routines, you need to have header information about who's doing this and who is your go-to person to find out why they did something. Joel Ivey was the original author, so he's the go-to person, but I'm the one who did the overhaul, so any problems with the overhaul are my fault and not his fault. So we're setting up the responsibilities, we're setting up what our version number is, what is this a part of, are we patched, are we released. We've got some header information that you want to put at the top of every routine in order to make sure that you can distinguish the routines from each other. Because as you break out these tiny, dense, abbreviated, old-style routines into readable, maintainable, annotated code, the number of routines is going to vastly multiply. You're going to be hopping between routines rapidly as you do programming projects. And so you need header information at the top that tells you immediately which one you're in and when it was changed. If you skip on this stuff, you will find yourself hopping between routines and thinking you're in a routine that you're not because you never bothered to change the description, and you start making edits to the wrong routine. Very easy mistake to make unless you do this simple step. Just keep your header lines up to date. You got to be clear about your version numbers. You need to start and maintain a to-do list. You will not be able to keep this in your head. You absolutely not. You absolutely have to have to-do lists to help you. So now, with that stuff out of the way, the first thing that you want to do, if we take a look at like XTER, right? The problem that greets us immediately is that it's a wall of text. There are only a few places where white space was introduced to create separation. It was one of the first lessons that I learned in my first programming class is, white space is an incredibly powerful tool for organizationally speaking because we're visual. And so if you follow the principle of locality and you put related things closer together and you separate unrelated things, it will intuitively help you not get lost in these great walls of text. And so my very first step whenever I see a routine like this is to go through, and anytime there's a new label, I throw in a blank line or two or three ahead of it, right? I want to separate the groups so that they start to look like paragraphs on a page. That'll help keep you from getting lost. And then, I know some people believe that if code was hard to write, it should be hard to read too. Other people should share the pain, but that's not going to fly when you're dealing with something as complex as this. You have to annotate as you go, and that means you have to be willing to write in human language to a human being at the same time that you're writing in computer language to a computer person. Anyone who has not read Donald Knuth's Literate Programming book, I commend it to you. It's one of the most important books for modernization of software. And one of the things he says is you have to treat all programmers as though active programming is a bilingual action. You must write your software in two languages, a computer language and a human language at the same time. Right? And then labels. In mumps, labels are incredibly important because mumps is a dynamic language in which there actually is no such thing as a static subroutine. Other languages declare subroutines, declare functions, declare procedures. We don't. We just have a label, and it could be called from anywhere at any time. Go-tos, do's, you name it. So the spots that are labels are incredibly important for figuring out what the possibilities for flow are, especially when you're dealing with legacy code like this that has so many go-tos. You have to be able to spot the label, spot the go-to, and make the connection to figure out that this code is jumping from here to there. So the labels all need to be called out and isolated. If you look at the new version of the code down below, you'll see that, P variable is separated with a little bit of white space on both sides. If we look at another one like XUEROBE, again, same thing, right? Now you look down at num errors, same thing. So that's the pattern that we want to follow. Subroutine terminators and fall-throughs. So see this go-to right here is actually bringing an end to the XTER subroutine. In other places, something might be brought to an end by a quit. When it just flows in like this, it's not as easy to see that you've reached the end. So I throw in white space around my terminators like this so that it's easy to see where they are. And that way, if you back out and you look at this visually, even you don't have to program any mumps at all. You could look at the modern version of the routine and you can tell in an instant where it starts and where it stops, which is a critical part of figuring this out. Fall-throughs, by the way, are incredibly important because they create, like go-tos, they create their own hazard. So if you look at this label here, %xtzdat, and you look at the line above it, you'll see there's no quit or go-to. So when you call xter, it starts here, but then it falls through to %xtzdat. But then here, even though dis is run right up against %xtzdat, there's a go-to at the end, so it doesn't fall through here. So figuring out that these two, although they're separated by white space, are a unit, but these two, although they're not separated by white space, are not a unit, this is the sort of thing that you need to be doing things to visually highlight. Comments. You should not treat comments as though you are going to do a performance at an opera house and everyone's going to judge you. You are not supposed to be producing polished text. You should make comments that are like your personal notes to yourself and to the next guy to come along to say, what do I know about this and what do I not know about this? You know, if you see a problem, you should, throw some asterisks in and say, problem. If you say, I'm not sure what this line does, you should put in a comment that says, I'm not sure what this line does. I did, right? Earlier drafts of this routine were peppered with comments saying, is this variable even needed here? Or why are we going here instead of this other label? Because you're not going to be able to remember all the questions that come up to you, but those questions are important. Your immediate intuitive responses as you go through the code are incredibly valuable, and you can use the routine as a scratch pad, considering especially the fact that you're going to go through this routine over and over and over in the process of refactoring it. You can go ahead and put in temporary notes now, knowing that on a subsequent pass, when you've read more of the code, you may be able to answer that question. And it may change what you do with the line. So annotate like crazy. Put your comments in there. Put your questions in there. Every subroutine, this is considered best practices. Every subroutine, you really should note the inputs and the outputs and anything you need to say about the algorithm to make it obvious how the algorithm works. So, for example, in numers, you'll see that I've here are the inputs that come in. Here are the outputs that come in. Now it's obvious that date and errors must be inputs and outputs. But if you look at the earlier drafts of the software, most of these labels have no parameter list. Variables were being passed through the symbol table, and you couldn't tell what the inputs and outputs were. It was only, at first I would put a header for inputs with a question mark and outputs with a question mark. And then as I went through the lines of the subroutine, I'd start to go, oh, this must be an input because it's not being set anywhere, but he's relying on it. So then I'd add it to the inputs. So you're sort of iteratively, step by step, incrementally, building up the information about this stuff. And if you do that, it's less intimidating. You don't have to have all the answers all at once, and you shouldn't feel bad about the fact that you don't have the answers all at once. That's okay. It's fine. You put in the answers that you have, and you put in the questions that you have, and you move on. Your goal is to quickly move on, handle all the easy stuff, and then come back on the second pass, and now that you know more about the routine, you'll be able to answer some of those questions that you had previously. Okay, subroutines. You want to treat... Yeah, go ahead. Yes. We're going to a quarter after, right? Yeah, I'm assuming quarter after. Are you? All right. Well, I'll see if I can hurry through this. So you want to think about your subroutines. Bertrand Meyer, who developed the software language Eiffel, wrote a book called Object-Oriented Software Construction, in which he talks about that if you want to develop tests for subroutines to figure out if they worked, you need to have a very crisp idea about what the subroutine is or is not supposed to do. You want to be able to express it in English so that a reader can do it, and you want to be able to express it in technical language so that you could write a test around it. And if you don't do that, it means you don't really understand your subroutine. So one of the reasons that I put a lot of comments in my code is that I'm attempting to establish the contract between the caller and the subroutine in each place. And that's one of the ways to think about the comments that go at the head of each subroutine. Okay, this is one of the most important steps. Standardize case and syntax use and do a detailed read-through. When you do this, what I'm talking about is you take a routine like this and you go to the very top and you work your way through line by line and you take everything that says capital N and you turn it to lowercase nu. and you change the K to a kill and a $J to a $job. You spell out in lowercase all the built-in language elements, and it's going to expand these lines, but it's also going to create a big difference between the built-in language elements, which are just the language itself, and your variables, which are all in uppercase and now are sort of standing out for you. It makes it much easier to read and parse the lines. So when you look at the code the way that it is now, you know, you could understand, new, set, quit. These are things that even an advanced user might be able to get some idea what you're talking about, but they're never going to understand S, G, D. This stuff is too cryptic. So you want to change the software in that sense. You want to go through and spell it all out and lowercase it and come up with a standardized approach. This is the next thing you want to do. When you get to the point where you have finished your first pass, and now in theory, all of your subroutines are separated from each other, they've got header comments, everything is somewhat readable. You may not really know what everything does yet, but you can now read the code, right, relatively easily. This is the time when you need to figure out what your interdependencies are between your subroutines. And so to do that, you need to make one of these. Now, hopefully, you're working on a smaller piece than I am with the error log. But the idea is that you figure out, here's XTER subroutine, and it falls through to %XTZDat. And %XTZDat does a go to back to himself, and he also goes down to do, and do also goes back up. So I'm creating a visual map of the calls. And I can see that %XTZDat goes to dist, but he does slist. So when slist is done, slist quits and comes back. So I'm distinguishing the difference between the spaghetti code and the nice, well-structured subroutine calls. I'm looking at the subroutines that are within each routine. I'm learning which subroutines are located where. I'm learning which subroutines, despite the fact that they're in separate routines, might actually be closely related because they call each other like crazy. I mean, when you're going into this, part of what you're trying to understand is what are not what we are handed is the physical subroutine groups where they happen to be laid out in the text. But what we need to learn is the logical subroutine groups. Regardless of which routine they're put in, which ones actually are related to each other, which ones call each other, who's dependent on each other. And mapping this out is when you can start to say, if I change do, I can look at this visually and figure out who's impacted. I can see which subroutines are going to be affected, right? And likewise, if I start into a process of cleaning this up to try to create less brittleness, to make it more malleable, I can be looking at what are the easy ones to tackle first, and what are the big problem areas that I should save for last after everything else is cleaned up. It starts to lay out your priorities for which are the easy problems to tackle and which ones are the hard problems to tackle. Just to give you a sense, this one is done. This one is not done, but this is what it looks like now. I replaced this with all these looping go-tos and interdependencies between routines with this, where I've got a simple interface routine, and each interface calls one block of routines that might call some subroutines, and it might call some other things elsewhere that are shared. But if they're shared, it's basically this routine over here is this routine. I'm calling back into the gateway interface routine. So it's easy now to see what the relationships are, the way that this is laid out, compared to the way that it was before. All right, so let's go back to, So you sketch a call diagram. We're switching from horizontal mumps to vertical mumps, right? So the mumps, the way mumps used to work, there was a penalty to be paid from shifting from line to line. Once upon a time, it was an interpreter running in live time, reading the code and turning it into assembly code. But now, there is no penalty to having multiple lines and shifting from line to line. And if we break up these long lines into multiple lines, then we've got room for comments. And also, we gain more power in terms of our flexibility for how do you express if-else conditions. There are a lot of tricks that were done in the old code to try to cram things onto one line that resulted in code that's very hard to parse. Mentally to think about, if this but not the other thing, but also this flag or this other flag, then we go here. Well, when do you go there? It's hard for a human being to keep those kind of complicated Booleans in their mind. But if you break that up into a separate set of tests, each with its own comment, somebody could now read the code and understand it. So replacing horizontal mumps with vertical mumps is part of modernization. And that's why when you look at the new code, these lines are mostly one command long, and if they're not, they might be 2 or 3, but not any more than that. Right? They're trying to be a short. All right. One more click on that side. All right, I mentioned rescoping variables. This is incredibly important. You want to figure out where your variables are actually used, and when you figure it out that a variable is only used in a certain subroutine, let me find you an example right I've got a good one here, I think. XUER OBVP. Uh, these variables are the inputs to queuing a task. They're not needed anywhere except on this line right here. So instead of having it all up at the top level, where I'm doing everything at the top and then doing it, I go down a subroutine level and new them and do the do command. And that way, when I hit the quit, these variables all go away, and I don't have to think about them anywhere else in this routine or any other. I now know that they have no impact beyond this local area. And we'll create do dot blocks even when we don't have to, even when there's not an if or a for or anything else, just to limit the scope. New them, use them, and quit and get rid of them that way. So it's a huge organizational principle for making this work. All right, let's switch to questions. Obviously there's more to go through. There's more of the process, but you've got the handouts. They've been distributed, so I'm willing to take questions. Break here and chat with folks.
So we had somebody who was asking about the use of the go-tos in your library routine.
Excellent question. Right. So let's talk about that. It was a high priority. When you're modernizing code, it's a high priority to get rid of go-to commands that are substituting for for loops, that are substituting for do's, that are substituting for other things. You want to use a for loop instead of a go-to loop. You want to use a do instead of a go-to if you can. And you basically want to strip them out because go-tos lend themselves too much to spaghetti code. And this was a key example. I showed you the diagram. You could see it was going every which way. There are teachers who will tell you should never use a go-to, but as Sam Habiel and others who've been in my classes can testify, that's not exactly what I say. What I say is you should avoid the use of go-tos except in two cases. There are two cases where a go-to is important. And one is where you are trying to keep the stack from changing depth. And an example of when you might do that is during error processing. If you're in the middle of handling an error, every time you change stack levels, you're throwing away variables. So you don't dare change stack levels. So that's one of the cases. The other case is this case right here. And this is where we've got a gateway routine. And other people in our other subroutines in our body of code are calling wmail. And there's actually no advantage to a do here at all because I don't need to remember the levels. This whole thing is just a redirect. And I'm trying to make it as fast as possible. It turns out the go-to is one of the fastest commands in any language because it translates to one assembly language command. Most third-generation languages commands translate to multiple assembly language commands, but not the go-to. It's a simple branch. So it is extremely fast to do this. And what it means is, people might complain, well, going roundabout to the interface routine and then back out to where you're going, surely there's an efficiency penalty. It turns out the answer is no, especially if you have a go-to as your dispatch here. There's really no penalty by doing it this way. So this is one of the only two places that I'll use a go-to. Good question. What else? What's in the chat? Somebody have access to the chats with the questions?
That was the big thing, and then where can they get a copy of the presentation, which has already been answered. So those are the ones that are in the chat.
Yeah, shoot, David. Oh, what's it say? So tell me. Yes. Yes. Yes, that's exactly right. And this is where argument when people give you hard and fast absolute arguments, they're almost always wrong. There's almost always exceptions. The truth is nuanced. And so a go-to command is a command to avoid for any purpose except the ones that it's ideally suited for. But for those purposes, it is ideally suited, and no substitute will do. State machines, there's amazing things you can do with state machine technology, but it requires staying flat. Right? It's one of the scenarios where you need to be flat. I talked about here annotating database accesses. So that's because when you use FileMan to look at your database, your data dictionaries, it's not going to be expressed in terms of some piece of some node. It's going to have a file number and a file name. a field number, and a field name. So in your code, when you're accessing things from the database, you should side by side with the technical access that's going on here, you should put the logical description of what you're grabbing there, and it will help you to manage changing to your data dictionary to make the changes in the code that go with them. What else? Other questions? Say that again. Oh, no, no, no. This has not been released because it's in progress. I'm most of the way to being done with the first modernization pass. The step of modernization that I'm on right now is I am about to translate all of my I/O from hard reads and writes to using the dialog framework. Last week, I brought up I finished my first pass on the new dialog code, and the dialog code is a switchable environment in which instead of doing a write, I call a subroutine that claims it's going to do a write, but it actually checks a flag to see should I write or should I stick it in an array or should I do both. And that same subroutine can be extended to say, or should I push it out to a file, or should I write it to a pipe or a channel? So it's a extensible framework for being able to route dialogue in multiple ways. The writer is done, and then it's also includes a loader based on DDIOL, the mumps the FileMan dialog framework, so that you can, instead of writing hard-coded text like please enter a date, you can create an entry in the FileMan's dialog file that says please enter a date, and you can call a subroutine to access that dialog entry and write it to the screen or to an array or what have you. And the big power of that is, first of all, it's table driven. It's no longer hard-coded. And second of all, the way the dialog framework works in Vista is when you sign in, you have a language multiple that says what languages you speak and which one you've currently selected. And that sets a local variable called DUZ sub lang, and DUZ sub lang it drives the dialog framework to access the correct translation of the text. So it is very easy, once something has been put into the dialog framework, to translate it into other languages. All the code will automatically start speaking that language if you've done the work. So I am doing that transfer right now. I'm in the process of moving my hard-coded text, which at present, the hard-coded text I've isolated to the bottom of every routine with this little dialog subroutine in preparation for that. So this all used to be in quotation marks buried up in the text above. Now it's all down here in a table because the very next step is to go create dialog file entries for each one of these things. So we're very close now to being able to pull this off. So I'm not going to release it until this is done. This is when this is done, we'll be done with the first pass of modernization. Yeah, shoot. Yes. Yes. Well, thank you. My pleasure. So I guess we have what, another 5.5 minutes because we're going till quarter after. So here's the thing: you should annotate pattern violations. If you violate the SAC, if you're writing Vista code, or if you're writing MASH code, if you violate the MDC pattern language, you should note that. So this has no SAC violation, so it just says SAC. But if it had SAC violations, I'd put a little tag down here. I'd list what the violation was, and usually a SAC violation, it's frequently the case that what you're doing is you're accessing some implementation-specific mumps feature. Like I might be accessing YadaDB's $ZUT to do timing information. If so, I would say $ZUT, and then I would point you to the page of the documentation where it's at. Because one of the principles to commenting is, if to understand this code you have to know something that you know right now, but that your reader probably isn't going to know, you should put it in the code in a comment. Because why make them rediscover what you've already done all the work to discover? So you can just point them directly at the line of at the page of the documentation that explains what $ZUT is, and then they'll understand what you're doing. And when I do that, I also cite the SAC file, the line of the SAC that says you're not supposed to do that, so that they can see that there's an issue. So from here, yes, yes, there you go. Sure. That's exactly right. That's exactly right. What you're going to see is that there is I'll go through these passes until in the absence of questions. I'll go through the rest of these real quick so you can see what they are. One of the passes that comes later after you've annotated the pattern violations is late in the process. You then arrange to have kernel or mash wrap up that SAC violation feature into a callable subroutine, and then change your code so that you don't have a SAC violation anymore. You call their subroutine. This is one of the purposes of the kernel, and one of the purposes of MASH is to make it so that you can access implementation-specific features without violating the SAC. We're supposed to collect all those together into one place. So, but you can't do that if you don't know what they are. So you should annotate as you go through and note any one that you've got, so that on a later pass, which we'll come to shortly, you can then get them out of there. So we talked about differentiating shared services, PPIs, private program interfaces. Building an interface routine we talked about. You notice it's step 23, and it's step 23 because you can't do this until you've done all the steps that come before. Until you know the relationships among the subroutines, it's not safe to start rearranging them. But once you've got it all sorted out, then you can build your interface routine, and you can start moving things out. You can move your pattern violations out to a separate library, which you invoke with PPIs, and then later you can push it out to the kernel or to MASH. You can, like I talked about here, move your text into a dialog $text table in preparation for moving it out to the dialog file. Convert your I/O to a dialog framework, right? So I've got all these XUERDW and DR routines that do all my reads and writes in preparation for calling the reader and the writer. Getting yourself to where you develop unit tests for these things, do any database conversions you're going to do. And then if you've got common library code, which we have in the error log, for example, right here, these are date-time conversions, right? And he doesn't have to have this stuff in here. This stuff is in kernel, it's in FileMan, it's in MASH. So the intent is that on this step, you should get rid of that code. So you can see I'm not done because it's still here. I haven't moved it out yet. But that's why it's not released. I've still got a couple more steps to do, but I will. And the reason is there should be as few people doing date-time conversions as possible. I mean, Y2K was supposed to teach us that, right? There's no point in reinventing the wheel over and over and over. Any pattern violations, you make the PPIs for those. You should update your manuals, which is where Kathy's going to come into play here and help us. And then you could release your first modern version. So this is how close I am to being ready to release the error log. And it's going to be released as part of VA PALS initially. Once that's done and you support it for a while, you'll find that you can fix bugs in this code much, much faster than you could in the previous code. Everything is self-explanatory. It's all spelled out. You don't need an expert programmer to fix this stuff anymore. You could have students fix it. Once that's done and reduced to a trickle, you can now work on your second version, which is the one where you develop your web interfaces and system interfaces, and you release that as your second version. At that point, your code is modernized. And this is how close we are to this on the error log. This took me 1 month to do this with the error log. So just imagine if we had a whole bunch of us all over Vista, each doing this with our own areas. We could modernize this in no time at all. We don't have to be afraid of this. Yeah, you just have to coordinate. You divide up the labor and you talk to each other. And that's how we can move from error logging being locked back here in the 1980s era to being caught up to 2019. Thank you very much. I would love to.
Bye.